let me let the show begin. I'll hand it off to our session chair. Oh, you have your own.
Okay, let's begin our first morning session. My name is Hye-Young Gi. I am a professor at the physics department here at University of Toronto. All right, without any further delay, it's 9:14, so I'm going to start. We have two talks in the morning before the coffee break. Our first speaker is Andrei Vrajitoarea from the University of Chicago, and Andrei is going to tell us the assembling and controlling photonic quantum matter, solid, fluid, and CATS.
Sorry. This works. Big button moves forward, bottom one moves backwards. And if you want to highlight anything, go ahead and use the very top button. Hold it down. Go to zoom and share screen. Oh. Yes, I do. Is it turn on? Yes. All right, thank you so much for the introduction. Giving the first talk means I have the pleasure to thank the organizers for putting together this wonderful conference on topical research on quantum information and quantum control, and also for giving me the opportunity to give a talk on our recent efforts of using superconducting circuits to find new ways of both preparing and controlling synthetic quantum materials that are made out of interacting photons. As a disclaimer, I've only started recently my position at NYU, so the results I present today is mostly work that I did in my postdoc position in the Schuster and Simon groups at Stanford. Okay, so a bit of background if the clicker works. No, sorry, I can use this. So a bit of, now I know why it doesn't work. So a bit of motivation why we're doing these experiments. We're trying to understand strongly correlated quantum materials, both from a fundamental perspective of trying to understand exotic phenomena and condensed matter physics, but also from a technological perspective in trying to use these collective quantum phenomena for different applications, especially for quantum information. And this is where, you know, trying to solve these systems when they're large, it becomes kind of a hard problem to do classically. So that's why there's a growing effort and interest to engineer these quantum systems. They can mimic the quantum phenomena of interest. And there have been a variety of platforms that you can isolate your quantum system and perform control. And the system that I'll be talking about is interacting microwave photons in superconducting circuits. Okay, and this is where the idea of a quantum simulator comes in. You have a model Hamiltonian of interest. You want to study the ground state, you want to find the ground state or study some complicated many-body dynamics. And there are generally two approaches to this. And both of them have, of course, their advantages and unique disadvantages. There's of course, the digital approach where you have a universal digital quantum computer where you're trying to essentially, the buzzword is you're trying to trilateralize your Hamiltonian by decomposing your Hamiltonian evolution in terms of single and 2-qubit gates. And this promises a universal quantum simulator, but with the caveat is that you need a lot of single and 2-qubit gates with low errors to be able to perform with good fidelity your simulation. And then there's the analog approach, where you try to implement your model Hamiltonian directly into the lab, where if you can do it, you can directly sample your dynamics in real time. The caveat is you have to be able to implement your Hamiltonian with the platform that you have in your lab. And this is the sort of approach that I like to take where I'm interested in building these analog quantum simulators with superconducting circuits. And this is where the circuit QED field, which is the circuit version of cavity QED, this is where both my PhD and postdoc groups, we've put together most of the tools for assembling these quantum materials made out of microwave photons. We can confine photons in lattices of microwave resonators where the lattice themselves have some interesting band structure and it imbues the photons with some form of effective mass. We can use the nonlinearity of circuits composed out of Josephson junctions to introduce interactions between our photons that otherwise don't interact. We can introduce dissipation to engineer reservoirs for officially thermalizing many-body states, and also we can introduce elements that can induce an effective magnetic field for photons to look at topological materials. But I'm not going to go into detail about all of these components. I just want to highlight the model, the system that we're working in our lab, which is a one-dimensional Bose-Hubbard model, where you can think of it as we are patterning a one-dimensional lattice where our particles, which are our photons, are tunneling between different sites, and they're experiencing strong on-site interactions. A strong energy penalty for having two particles in the same lattice site. And this competition between the kinetic energy and the interaction, as the experts in the audience would know, this gives rise to some strongly correlated phases for a Mott insulator and a superfluid. So this is the model, and this is what we expect to see in the model, but how do you actually implement this in the lab with superconducting circuits? This is what I want to go over briefly. Since we're dealing with bosons, it seems quite natural to implement our sites as harmonic oscillators, where we can confine our microwave photons. The simplest object we can make in the lab is essentially what I've drawn here, an LC oscillator, but we also want to introduce interactions, and just having an LC oscillator is not enough to have any types of interaction. And there are many ways to introduce interactions in our circuits, but the easiest approach is to just replace that inductor with a Josephson junction. And this Josephson junction, you can think of it, it creates this anharmonic energy spectrum. You can either think of it as a particle that's now confined, that was previously in a parabolic potential, is now in a cosine potential, and it gives you this anharmonic energy spectrum. Or I can just think of this junction as a nonlinear inductor that changes its inductance quite a lot, by about 40% every time you introduce an additional quanta of electromagnetic energy. Okay, and this is an important tool, obviously, for quantum computing, because this allows us to resolve and perform quantum control on the lowest two energy states. That's our qubit. But for what we need to do, this is how we're using the nonlinear junction to create sort of these contact interactions in our site, where we have this energy penalty that is the anharmonicity to add an additional photon in this lattice site. Now, you can't do interesting physics if you just have one object. You need to couple them to form an artificial lattice. And the easiest thing we can do is just to couple our qubits, which for the experts, if people want to know these, we call them transmont qubits. We couple them through a capacitor. And if we think about the electromagnetic energy stored in that capacitor, we can model it essentially as having our photon. If we put a photon here, it will essentially tunnel between two lattice sites. And this is exactly what we calibrate in our measurement. Okay, so if we put together these two ingredients, then this gives us our one-dimensional Hubbard model, where the transmont qubits are these blue crosses I'm showing in this optical image, right? So these are the lattice sites of our tight binding lattice, where our microwave photons, our quantum particles, are tunneling between each lattice site, and they're experiencing strong on-site interactions. When we pattern our circuit, both the tunneling energy J and the on-site interaction U are fixed. These can be tunable, but for our system, they are fixed. And the only thing that we can tune, but it is quite a rich tuning knob, is the on-site energy of each lattice site. So we now have control over the lattice potential, and this allows us to create quite interesting many-body states. Okay, so just briefly showing you the full device. I showed you the tight binding chain of transmonts. This is where you can think the lattice is happening, the science is happening. One thing I glanced over is the fact that we don't just have one junction, but a loop, a superconducting loop. That's a square bit as we inductively couple bias lines to each qubit. This allows us to, through a magnetic field that's spreading the loop, allows us to tune the Josephson energy of our Josephson junction. It allows us to essentially tune the effective inductance of our qubit, and therefore we can tune their energy levels, and we can tune in real time the potential profile of our lattice. And we can also do site resolved microscopy, where we can tune each individual transmon to its dedicated microwave resonator. There are different energies, but through what's known as the dispersive regime of cavity QED, this allows us to probe the occupation and any type of operation in the Bloch sphere, any type of observable in the Bloch sphere of the transmon by just probing the dispersive shift and essentially the homodyne response of our oscillator. So this allows us to measure the occupation and other forms of coherence functions for each individual site. So what are the parameters of our circuit? Well, let's start off with, so we compared to the lifetime of a photon to be in our lattice, our tunneling rate is about 3 orders of magnitude faster than that. So we're in the coherent quantum regime, and our interaction energy scales, the anharmonicity, is an additional order of magnitude larger. So we're in the many body regime. And for the experts in the audience, this is what we call hardcore bosons, where on-site interactions are greater than the tunneling energy. All right, so there are many groups in the world that are focusing on putting together these circuits to create these Hubbard models, these synthetic materials. But putting together these circuits is obviously exciting, but it's only the beginning. It's only the first step, the first journey, because what's equally important and actually very challenging, and it's sort of the whole topic of this conference, is that you want to build tools to sort of target certain many body states. You don't just want to put in particles and they just let them disperse and look at some properties, but if you want to target specific many body states, that becomes a challenging problem. It becomes a many body problem where you're trying to prepare some entangled state and think of ways in which you can control it. And this ties into not just many body physics, but also quantum information and quantum enhanced metrology. And even if you prepare this entangled state, you can think it still becomes a challenge as to how to efficiently probe it and confirm that you've prepared a target state that you wanted to prepare. And this is sort of the main scientific thrust of my previous postdoc group, but also of my group as well, where we're trying to come up with new preparation schemes as well as new types of probes and control techniques. And I'm just going to briefly glance over a few of them, some work that we did where we use both dissipation and disorder to prepare solids and fluids of light, and also using site resolved control to actually prepare superposition of a solid and a fluid, in which and using site resolved control to even see how that maps to a highly entangled state that we can try and probe using a single qubit using a many body version of a Ramsey interferometer. Okay, so how do we prepare a solid, in this case, a Mott insulator for photons using dissipation, where we have this object, which is a qubit that has to refill itself with a photon every time it's empty. How do we do that? Well, we just use optical pumping plus dissipation. We have a 2-photon transition that excites the 2-photon state of this object that we call the stabilizer, and then we introduce energy-dependent dissipation, where we introduce a very leaky LC oscillator that's resonantly coupled to the 2-to-1 transition of this anharmonic oscillator, and this allows us to always stabilize the state to the 1 Fock state. Now, if we couple this stabilizer to our lattice, then this allows us to shuttle photons into our lattice until we reach 1 photon into each lattice site. And this is how we stabilize an insulator, a Mott insulator, where the filling front, the filling dynamics stops, it's suppressed, because now we have to pay an interaction energy, which is our many body gap, to be able to put in an additional particle in this insulator. And this works quite well, not just for Mott insulators, but any type of incompressible phase of matter where you have this robust many body gap that prevents you from interactions, that prevents you to put in an additional particle. So that's how we prepare solids, but how do we prepare fluids? Specifically, how do we prepare compressible states of matter where you don't have this robust energy gap? And the way we do that is we use a different type of ingredient, different type of what you normally call a flaw in our system. This is where we use disorder, or more specifically, site resolved control of our lattice sites. In this protocol that I'm showing here, where on the left, we detune our lattice sites, our qubits far away such that we're suppressing tunneling. In this regime, any type of multi-particle state is just a trivial product state, which means that we can easily prepare it by localizing photons into specific lattice sites by applying the appropriate calibrated microwave bipulses. Then next, what we do is we slowly bring the qubits into resonance, and we do it slowly such that we're following an adiabatic trajectory such that we're always staying in the same instantaneous eigenstate. And this allows us through tunneling, so this allows us to start from localized photons in the disorder regime and delocalize them into a strongly correlated fluid through tunneling enhanced quantum fluctuations. And then we detune the lattice sites very fast and perform our measurements of population as well as coherence. Okay, to benchmark this method, we can look at the single particle picture, where here I'm showing you the eigenstates and the eigenenergies as a function of disorder, where because of the adiabatic trajectory, there's this one-to-one correspondence between where we put in our particle and which quasi-momentum state we delocalize into. And this is the data showing you where I'm doing snapshots of the density profile along different disorder implementations, where we start with a photon that's localized in this qubit. And then as we slowly decrease the disorder, now we can see that it delocalizes into the lowest order quasi-momentum state. So this is the single particle benchmark. Now we can also do this for free particles. Here I'm showing you the spectrum, the calculated spectrum of eigenenergies for the free particle band, where for strong disorder, we start with free particles, the highest energy free particles that are localized here, and then we ramp down the disorder to near degeneracy, and we can see in real time how these particles are delocalizing as we look at different density profile snapshots at different disorder strengths. And here I'm showing you the same thing for density profiles for 2, 3, and 4 particles as you're going from a delocalized regime, from a localized regime to a delocalized regime. And one interesting thing is we see that the density profiles, they change as a function of the filling fraction. And this is where interactions play a role, because if you do some quick calculation, if you assume your many-body wave function has just some confinement but no interactions, then obviously all the density profiles should have the same shape, mimicking a single particle response. But now if I add a little bit of, if I add infinite contact interactions in my wave function model, then I can see that I'm reproducing the right density profile. And this shows you that indeed the interactions are shaping the density profiles of our fluids. But another more concrete way to look at how these particles are interacting and delocalizing and they're ordering themselves is to look at this, at something that people in our field use a lot. They're looking at strongly correlated materials, which is a paired correlation function, which is a probability of simultaneously detecting 2 particles being present in the lattice at some finite distance x. So a G2 measurement, where here I'm showing you the data for different filling fractions, where you can see that there's a spatial anti-bunching where G2 is less than 1 that scales with the density. The insight there is that as you put in more particles, they have less space to delocalize out to before they start to interact with their neighbors. And now if we rescale this data, this axis of space with the density, we can find that our correlation functions are all matching a universal curve that for the experts in the audience, this is a model for Tonks-Girardot gas, which is a gas of bosons confined in one dimension, subject to strong infinite contact interactions. And you see some weak oscillating correlations. That is just a sign of what are called Friedel oscillations. This shows you that there's some weak crystalline order because of the large contact interactions. And we observe this. And this is a sign to show that as you're confining your bosons in 1D, they're acting as fermions due to the interactions. Okay, so for this last part of the talk, I forgot when I started, but I'm guessing I have 5 minutes? 6? Okay. Okay. 6 plus 5. Okay. I was looking at the clock. I assumed I started 10. Okay. Yeah. I'm going to talk slowly now. I apologize.
Need more time for questions.
Oh, yes, that was, people should feel free to stop me now that I have more time for questions. I should have said that at the beginning. Anyway, so for this last part that I'm gonna go slowly over, hopefully not too slowly, is I want to change gears a little bit. And the way we were kind of thinking about this new direction is sort of asking something that might be vague, but more of a fundamental question is how can we interface quantum computers with these synthetic quantum materials in a way that we can maybe come up with new techniques for probing and controlling them. Okay, but that's vague and very general and maybe too broad. So, but let's go back to the quantum fluids that I just browsed over probably too quickly. And despite the fact that we're preparing something out of, in our circuit with some photons that are quantum particles, you prepare some quantum eigenstate, the control itself is classical. What do I mean by that? Well, we're using side resolved control, but we're doing it with some classical waveform generator in the lab, and we're biasing some classical currents to our qubits, as I described before. But the lattices themselves are quantum mechanical. So then we ask this question, can we use the quantum nature of the lattice itself to perform quantum control of the lattice configuration? And if we can we actually leverage it both to look at maybe different types of dynamics in the system, or maybe prepare some interesting entangled states that would be otherwise hard to do if you just had classical control in our system. Okay, so this got us thinking more in the direction of looking at transport and how we can look at transport of particles and condition that transport through a lattice configuration that now depends on the quantum states, the quantum state of one, or you can think of even several qubits. So now you can have a lattice configuration that is a superposition, a quantum superposition of many configurations. And this presents an interesting prospect of now being able to interfere different unitary evolutions in our system. And so the simplest case, so then trying to dissolve this even more and trying to think of probably what's the easiest thing that we can demonstrate, which is maybe having a lattice configuration that depends on the quantum state of one qubit. Well, that's kind of sounds like a transistor, but for photons. And here I'm showing you this cartoon where the idea was, well, what if we just have photons or some many particle state on the left-hand side of our lattice, and then we can do some adiabatic control where we bring that state or those sites to go lower in energy, such that if we were to satisfy the adiabatic theorem, in principle, they should shuttle over to the right-hand side. But now, can we engineer this transistor where now the shuttling, this transport, is now conditioned on the quantum state of this middle site, which we call our ancilla or control qubit, where this transport or this transfer, this many-body state is conditioned only on this ancilla having a photon. And if it's empty, then you still keep your initial state on the left-hand side. So that's kind of the cartoon, but let me go over the details of the protocol. So we start with photons in a 7-site lattice, free photons on the left. It's disordered, and then we bring the lattice sites as we did before in a near zero disordered configuration, but now it's a different configuration. Not all the sites are resonant with each other, but you have this middle site that is our control qubit. We have this middle site that is now detuned by its interaction energy. What does this mean? This means that now our transport of particles from the left to the right is mediated through tunneling through the 2-photon state of the control qubit. But now this resonant tunneling is conditioned on having that ancilla sign being occupied with a photon, because you can't occupy the 2-photon state if you don't originally have 1 photon in that lattice site. So this was the idea, transport mediated by the 2-photon state implies that now your transport is conditioned on this control qubit's quantum state. It has to be in the 1 state to tunnel through. So in this case, what I've drawn, this middle lattice site is completely empty, which means that even if I remove this order to a configuration where it's inverted, so the left sites are at lower energy, these free qubits are still excited on the left. Nothing happened at near degeneracy in this transistor configuration. I essentially have a solid. It's a mod insulator where there's no tunneling on the other side because the ancilla qubit is empty. Now this changes completely now if I put a photon in the ancilla, and now you have that this 2-photon state mediates the delocalization into a fluid. Okay, and then if we introduce disorder and follow this adiabatic trajectory, now my free photons are on the right-hand side. And this is an interesting way to say that actually we've made a conditional few body swap operation. But now this control qubit is quantum mechanical, so it doesn't need to be either a hole or a particle. It can be a superposition of a particle and a hole. And this is sort of what we originally envisioning as the hallmark of this photonic transistor, because now if I originally start with photons on the left, but now I have a quantum superposition of essentially our lattice configuration going to this transistor configuration, our photons are now in this lattice are now prepared in a coherent superposition of being in a solid and a fluid state. And now if we adiabatically reintroduce disorder, then now this solid plus fluid superposition corresponds to this highly entangled Nuon state, or you can think of it as a cat state, where I have this coherent superposition of having free photons localized on the left-hand side plus free photons localized on the right-hand side. Okay, and you might ask, well, we use this ancilla to prepare this highly entangled state. Can we ask more of this ancilla qubit? And the answer is yes. We're going to use it also for benchmarking the long range to measure the coherence of this highly entangled state. How do you measure coherence? Well, I assume most of you know that the idea behind the Ramsey interferometer, but we use it a lot as qubit people. We prepared the qubit with a pi/2 pulse in the Bloch sphere, let it process for some amount of time, and this allows us to measure some Ramsey fringes shown there that gives us two pieces of information. The frequency tells us the energy difference between the spin up or spin down. This essentially tells us it is a perfect way to calibrate the qubit frequency in our experiment. And the fact that we're seeing oscillations implies that this is indeed a coherent superposition of 0 + 1 or spin up or spin down. The many body version of this would be to perform this entangling operation that I described previously. Now let the system evolve for some time delta t to accrue some relative phase between the two components of our cat that is proportional to their energy difference. And then we disentangle by performing the reverse transistor operation to move all of that phase information into our control qubit, our ancilla qubit. And if we measure now the Ramsey fringe, it is much faster because now it's not just processing at its reference frequency, but now it's also processing in the energy difference between the left component of the cat and the right component of the cat. If we do Fourier transforms, we can see that indeed this energy difference, right, this precession frequency difference corresponds to the expected energy difference of our two cat components. And this again verifies that we have entangled state for two reasons. Well, it's definitely coherent superposition because we're seeing coherent oscillations in our Ramsey fringe, and the energy matches what we would expect for this Nuon state. Okay, and let me wrap up, since I think this is the last minute, by trying to benchmark the entanglement in our system to see how it can be used as a sensor. And the idea is that, okay, you have this Nuon state. What people normally do with entangled states in general is you try to make them very sensitive to external parameters. Now, with circuits, we have many external parameters, but like let's control be introduce something. And here we do this for both 5-qubit cats and 7-qubit cats. We intentionally detune some qubits below by minus delta and above by plus delta. And now we look at the Ramsey fringe frequency. We only have to measure 1 qubit to determine what is our sensor detecting. And we can see that the Ramsey fringe frequency has this collective enhancement in the phase that that single qubit accrues. And this collective enhancement essentially scales by measuring the slope of the Ramsey frequency as a function of this designer perturbation, has a slope that exactly matches the system size of our cat. And this sensitivity that scales with the system size is exactly the Heisenberg limit that essentially dictates the fundamental limit of how sensitive you can be allowed by quantum mechanics. Okay, so with that, I just want to wrap up saying the other things I did not cover, but we're hoping to add more and more lists to new types of preparation schemes and new types of probes and control. I'm happy to talk about it more during this conference. Let me quickly acknowledge my former postdoc lab. the PhD students that I worked with for the quantum simulation projects, our TV collaborator, Caden, our PIs, David and John, and also advertise I'm starting my own group at NYU, where been there for about 6 months, but things are going smoothly, looking for students and postdocs, having fun building the lab piece by piece. So stay tuned. Thank you so much and happy to take any questions.